Now let's see relation between traction and stress. So till now we have understood the concept of traction and stress. So qualitatively we understood what is traction and what is stress. And now let's see the relation between traction and stress. Okay. From traction, how can we find the stresses? Okay, so let's take this is the cut plane which we always talk about for the traction, for the definition of traction. And on this surface plane or reference plane there is a traction acting, okay, which is denoted by Tn, and N stands for the surface normal. Okay, so as we know, the traction always acts at a point with respect to surface normal. So we need to define that surface normal, which is described by N. Okay, and let this surface normal, okay, this reference plane, okay, we need to define the reference plane. So the N, okay, this N is different, okay, and this N is different. So this reference plane, let's define the orientation of this reference plane as LMN or direction cosines is equal to cos theta 1, cos theta 2 and cos theta 3. So now we have defined the traction and its surface normal, okay, with the direction cosines. Now let's see, no, let's describe the stress. Okay, let's take this point, okay, this point, this point is somewhere here, okay, and this triangle, okay, around this we can take infinitesimal area. So let's take this triangle. Let me give numbering, not numbering, but OABC, OABC. So this ABC, this triangle, okay, it is infinitesimal area on which the traction is defined, with respect to which the traction is defined. And this infinitesimal area is the orientation is also like LMN, cos theta 1, cos theta 2, cos theta 3. Okay, so the orientation of this is same as the surface plane, right? So LMN. Okay, so now we have defined this traction plane. Now let's define the stress or describe the stress. So we need an infinitesimal volume. Okay, so if you see, I have just superimposed, there is a infinitesimal volume which is superimposed uh, on this infinitesimal area. Okay, so to describe the stress. Okay, so now you can imagine that there is a red color. This volume represents infinitesimal volume. Okay, and our point on which the stress we want to define. Okay, that point is sitting somewhere inside this volume, but on the infinitesimal area. Okay, so O, A, B, and C. So now you can understand this ABC is a traction plane, okay, and OAC, this triangle, this face OAC, then OAB and OBC. These are these three faces, okay, they are the faces of infinitesimal volume on which the stresses are acting, right? So we have seen the how stresses are acting on the faces of cube, right? So you can imagine that this OAC, OAB and OBC. So here I have showed here O, A, B and C. Okay, so OBC, this face on which the stress sigma 11 is acting, right? We know, we have seen the stress components here. Okay, sigma 11. So on this phase, sigma 11 is acting. So I'm taking there are nine stress components, right? Nine stress components. I'm taking three stress components which are acting in direction of x. Okay, and we know what are so x direction stresses. What are those? They are sigma 1 1, sigma 1 3, and sigma, let me write it in order, sigma 1 2 and sigma 1 3, where this first index 1 1 1, it denotes the direction of stress. So I have showed the same thing here. The direction of stress, sigma 1 1, it will act on OABC plane, okay, or OBC phase. Then sigma 1 2, okay, this sigma 1 2, it acts on plane or phase OAC. Okay, since I have written it outside because it's very messy, but you can understand it. This sigma 1 2 acts on this phase. Okay, similarly sigma 1 3, it acts on a OAB plane or OAB phase, okay, which is also again showed outside. uh, so sigma 1 3. Okay, so now I have all x direction forces. So now what we are going to do, uh, we need to find, so we have Tn, right? Tn can be resolved into three traction components, as we know: T1, T2, and T3, right? And this is, let's say, Tn. So this is going to be my T1. Okay. Okay, so given this, we want to find the relation between traction and stresses. Okay, so how we do? So we just simply take the equilibrium of forces. Okay, force equilibrium. So first, taking equilibrium about x-axis. Okay, summation of all the forces in x direction is 0. Okay, so we can take the x direction force due to traction T. Okay, so this is Newton per mm square. So we need to convert this into force. So force due to T1 is T1 and this area ABC. Okay, delta AN. That is my force due to traction, and minus other forces due to stresses. So sigma 1 1, which acts on OBC phase. So sigma 1 1 into the area of that OBC phase, okay, which will be delta A and cos theta 1. So it is just this big triangle, the infinitesimal area. We can take the cost of cosine direction uh, of that delta n, and we get OBC area. Okay, so this is the area of OBC, and stress into area, we get force due to this sigma 1 1 stress. Similarly, we can get on this OAC phase, okay, the force which is stress into area of that phase. And similarly OAB phase, so the stress into area of that phase. Okay, so now we have four forces on four different planes or phases. Okay, so this force from traction T1, and these three forces from stresses in x directions. Okay, so when we just solve this, okay, we get this cos theta 1 is equal to L, this is M, okay, and this is N, and delta N gets cancelled. So we are left with T1 sigma 1 1 L plus sigma 1 2 M plus sigma 1 3 N. Yeah. So this is the equilibrium in x direction. Similarly, we can do equilibrium of forces in y direction and equilibrium of forces in z direction. We get T2 and T3 in terms of other stress components. Okay. So we got these three equations T1, T2, T3 in form of all uh, nine stress components and orientation of that uh, face, okay, or normal surface normal. Okay. So this is the relation between traction and stress. Okay, this is the relation we have got. And these three equations, okay, equation 1, equation 2, and equation 3, okay, we can write it in matrix form. Okay, we can simply, if we put it in this order, we know the matrix multiplication rule. So we can write this left hand side t1 t2 t3, we can put it in vector t1 t2 t3, okay, and this sigma 1 sigma 2, all these stress components are multiplied with direction cosines lmn, right? So lmn, this is a direction cosine vector, and these are our stress components. Okay, so this is in matrix form. We can say this is a traction vector. Okay, this is a direction cosine, okay, direction cosine vector, okay, of that infinitesimal area or surface normal. Okay, and this is our stress matrix, okay, or we can also say stress state. Okay. And this is in matrix form. In tensorial notation we can write T is equal to sigma dot n. Okay, so this is in tensorial notation. Okay, then next section we will see using this relation between stress and tensor. We will see how we can understand the principal stresses and how we can derive the principal stresses.